This is Smith chart. We are going to use this for the previous problem to solve in it. Just have an idea, then we will go with in a magnified case. See, I am going to increase the size with something large. Then you go with the bottom scale of the Smith chart. This is a standing wave ratio. We have first scale for the standing wave ratio. When you are moving this direction towards generator, when you are moving this direction towards load, then here reflection coefficient either E or I, current or voltage. We are going to now use these two. Remaining will be some other applications. On this left hand side we saw when you move to the right hand side, by decreasing the size here, see here also transmission coefficient existing, transmission coefficient SWR, and here also some parameters are existing. For those parameters we are going to use all these scales. Here we are going to use SWR scale and reflection coefficient scale. Then we will move to the upward direction. See, in this case already you saw these concentric circles we call it as a resistive component. Concentric circles in resistive components. R by Z0 is a normalized one, or conductance components G by Z0. This is the resistance, real part. We are going to refer this axis, resistive part for this real axis. When you move to this, all these circles like this arcs you are finding above to this reference line, we are going to use all these for the complex, means imaginary part. These are the positive values. When you come to the down, here all these we are going to use for the negative values. Capacitance component, inductance going to be used here. And see, one more parameter on this, wavelength. Here, see, are you able to see this letters? See, wavelength towards load. This is wavelength towards load. In a similar fashion, when you move up, here, this one, so just having these see, towards generator. When you are moving in upward direction towards generator, when you are moving in downward towards load going to be observable. So this is Smith chart is somewhat difficult to see in a PowerPoint presentation or else within a laptop. Just by having this hard copy you look it if possible to you. Otherwise through this problem I will introduce this Smith chart to you. Then this is the Smith chart. Now we will go with the problem. What is the problem we saw? What is the Z0 given? Z0 given as 50 ohms. ZL is given as what is the value of ZL for the given problem? 5 plus J 2.5. I think 50 I had given. You carry it as a 5 plus J 2.5. Then we are going to have this it as a normalized ZL. Normalization means you are going to divide that by Z0. When you are going to divide this entire thing by 50, 5 gets cancels, then 1 by 10 equal to 0.1. Here 5 5s are by 10 equal to 0.5 we are going to get here. So ZL plus ZL up to this part, then we will come to the next point. See this. So what is the impedance given ma? Impedance in a normalized form is given it as ZL by Z0 equal to 0.1 plus J 0.5. 0.1 plus J 0.5. So on the real axis, already you came across this x-axis going to be for us our convenient. X-axis will give you real axis, then that arcs like curves will give you imaginary part. In this case 0.1, see this 0.1, this line will follow that, this line will follow that 0.1, this line is going to follow 0.1, and see this J is going to be 0.5, so that this 0.1 real axis is going to coincide with this 0.5. So here we are marking that it as a normalized load impedance, ZLN you can write. Then see this, looks like this. What I have done, ZL going to be ZL equal to 0.1 plus J 0.5. So this is the real axis, 0.1 circle coincides with this 0.5 imaginary axis. So we identified load impedance on the Smith chart. First step we finished. Then we will go with this origin. Already we gone through that 0.1 axis. From the center, 0.1 axis, from the center you are going to make, this is the center of this center 1, 0.2, 0.4 like this, 0.2, 0.4 like this. Here 1 to 1.2 we are going to have a 1 is the middle value. This is the center. From the center to the point whatever we marked here as ZL equal to 0.1 plus J 0.5, a length going to be considered. With that radius we are going to make one circle here. We are going to make one circle. That red in color will show you. We are going to, with this radius, the distance between origin to the point marked here ZL, normalized ZL, we are going to make a arc here. That circle is nothing but VSWR circle. We call it as this entire circle we call it as a VSWR. If you know the load impedance on the Smith chart, we can draw VSWR circle we had drawn. See that this is the VSWR. Then with that VSWR, where this line 0.1 arc or circle going to be extended. Already we have a scale in the bottom. We are extending this tangent to the scales. Onto the scales we are extending. Then this will become, this is the VSWR circle. With that, by joining this by just straight line, when I am making a snap it was somewhat tilted, not more. Here I am using a scale. From this point to here I am going to join. Now I am going to find out that this is the SWR in dBs. The third scale is nothing but reflection coefficient. This is SWR. This one is going to be a reflection coefficient. I am going to mark those values. This is the line whatever I had drawn here with a pencil. Then in the SWR here, see this, I am going to give with a magnified scale in the next. I am going to point out this by a magnified scale. See, this is the magnified scale. From 10 to 20, my tangent going to cross here. I am going to divide that into 5 parts. For part 1, part 2, part 2, part 4, part 5. So the distance between 10 to 20 was bisected into 5 parts. Then each part will become 10, going to be divided into 5 parts. Then each bisected part will be equal to 2. So that here I am going to get it as a 12. In the similar way, reflection coefficient, this third line. First line will give you SWR, the third line will give you reflection coefficient. Here this reflection coefficient 0.8 to 0.9. The difference between these three points 0.8 to 0.9 will be equal to 0.1. 0.1 going to be divided into 5 bisects. 1, 2, 3, 4 and 5. Each one will become 0.02. Then from this side 0.8, from this side 0.8 to 0.84. So SWR will become it as a 12 and reflection coefficient will become 0.8 plus 0.2 plus 0.2, 0.84. I will show that there with a value. So this is the scale. I am marking it as a VSWR equal to 12 and reflection coefficient at this point will be equal to 0.84. Reflection coefficient will be equal to 0.84. So what we have done, first we marked ZL, normalized ZL on this Smith chart. After that I am going to make a VSWR circle. That tangent was extended onto the scale. I had found 2 parameters relevant to transmission line. That one is the VSWR, the second one is going to be reflection coefficient. Then our graph looks like this. See. So this line extended, VSWR found, reflection coefficient going to be found. After that we are going to make a straight line from the origin which is passing through the ZL and crosses these two. What are the two? This is going to be, this one going to be wavelength towards generator. The second one going to be angle, wavelength towards load, another one. Then this is going to be angle, angle of reflection coefficient. See, here I will magnify one more time. I will magnify. Come to the right side part. It will give see here. See, angle of reflection coefficient in degrees, angle of transmission coefficient in degrees. Here we are interested to find angle of reflection coefficient at input side. So that we have to draw a line. Which is joining from the origin through the ZL, which is going to cut that reflection coefficient angle. Just now we found that reflection coefficient as, what is the reflection coefficient we got? Reflection coefficient equal to 0.84. Then we have to find out the angle of reflection coefficient. For that purpose we are doing this by drawing this straight line from this point to this point. See here, this was cut at an angle of the angle between 120 130. This also bisected into 5 parts. This is, what is the difference existing between 120 and 130? 10 existing. 10 divided into 5 parts. Each one will be each one will be 2. So 122, 124 and 126. So angle of reflection going to be 126. If you extend the same scale at this, it will cross that. Here this scale you are going to refer. This is the wavelength at that ZL, which is, what is the value here? From 0.07, and this also going to be divided into 5 by 6. So it will become 0.072, 0.074, 0.075. So wavelength will become 0.075. Angle of reflection will become it as 126 angle of reflection. Then we will move to the regular graph, which is clear for you. So see that extended line from the ZL onto the angle of reflection and wavelength. This is the wavelength, this is the angle of reflection. See that values. Okay. So those values are not mentioned here. Can I reduce that size? That may give, no, not mentioned. So you remember that this is the value of 0.075 lambda. This one going to be 126 degrees. Next we will mark those. Then we are moving on the graph. We are moving on to the right side towards generator. You know the characteristic impedance was given to you. You are moving towards the generator. What is the length of wavelength transmission line given? 0.1 wavelength or 0.1 lambda. So that already existing lambda given as 0.1 lambda, Z0 equal 50 ohms, ZL equal to this, normalized one this. Actual length will be added, ZL, normalized ZL plus length. What is the normalized ZL wavelength? Just now we observe 0.075 lambda plus 0.1 lambda. It will be equal to 0.175 lambda. 0.175 lambda. 0.075 is existing on the left side, and by adding 0.1 length it became 0.175. See this scale. We are moving towards right side, means towards generator. So this point was marked 0.175 means 0.172, 174, 175. 0.175. See this one. Then from the left side to right side you shifted 0.075 lambda existing on the left side and added with 0.1 lambda, it will become 0.175 lambda. That was shifted towards, what it means, from the load side towards the generator side you shifted. That value was, wavelength is given as 0.175 lambda. If you join this point to the center, that will cut the VSWR circle at Z in. This one is going to be ZL with a difference of 0.1 lambda. You are going to reach to the Z in. So this was the scale, you can see. So you are going to join that ZL point wavelength angle reflection coefficient you found. Now with that wavelength you are adding with the transmission line length, you reach to the Z in wavelength. That Z in wavelength extended to the origin, you are going to get that Z in. What is the Z in value? See this Z in. What is this arc indicates? This arc is relevant to the not clear here, 0.4 real axis, and this point is going to cut this reactance component will be equal to 1.9. I will show that in the next graph. I think I was shown. See, I will increase the size. See this. This point was extended towards the origin. this mark will give you on the VSWR Z in was calculated or observed. Then see this line going to join 0.4 real, sorry, you come to this 0.4, that may also clear, but it's comfort to observe here 0.4 real. Then here this arc will give you, this arc will give you that, what is the value? By magnifying only we can understand. Just I will make it 150. See this arc 1.8 to 2 means 1.9 in between value, so that Z in was given as Z in 0.4 real plus J 1.9. With this few parameters we observed. So by this way we can calculate so many parameters about transmission line. What are the parameters given? Lambda given for you, Z0 given for you, ZL given. From that we gone through normalized. Then we was drawn a VSWR circle, and that was extended, that tangent was extended onto the scale. We found that VSWR reflection coefficient. Then we gone through that reflection coefficient, angle of ZL and wavelength of ZL at what ZL existing. Then it was towards generator was moved. Then we found out that Z in, reflection coefficient of Z in we found. If you extend these lines we will get admittance. Up to this, just a brief out of how to use a Smith chart. Just a complete diagram you have to go with this. This is the diagram, not a clear for you. Okay, see this. First what we have done, we marked this ZL. Then we draw the circle from the origin, VSWR circle, extended VSWR and reflection coefficient. The reflection coefficient angle and reflection coefficient wavelength found. When you are moving towards generator, you are interested Z in, so that you are moving. What is the length of you think this is the length of the transmission line, that will be added here to the existing point. You reach to that Z in reflection coefficient and Z in wavelength. Z in wavelength extended, that Z in wavelength extended onto the VSWR circle will give you Z in. If you extend these lines you will get it as admittance. If time permits we may go for the further problems or numerical problems on Smith chart. But if you have any doubts, if you are interested further few problems, you ask me. With this we are going to wind up our 5th unit. This is the 5th unit. Very important problem here. Okay, practice well and do better things in your assignments submission in the next, means assignments, not assignments, test, practice test you have to do. Okay, here I will stop.